The wings shouldn't have worked. That was the conclusion written in careful German script across technical evaluation documents in the spring of 1944. Engineers at the Rechlin-Leertz test facility stood before a captured American heavy bomber, measuring every panel, every rivet, every structural element, and what they found defied everything they understood about aircraft design. The wing was too thin, too long, too efficient to survive combat. Yet there it sat, evidence that thousands more just like it were crossing the Atlantic to rain destruction on the Reich. Welcome to the story of how a single captured B-24 Liberator forced German engineers to confront an uncomfortable truth, not just about American technology, but about the outcome of the war itself. If you're fascinated by military history, consider subscribing to our channel and let us know in the comments where you're watching from today. The bomber in question had a name. Her crew called her Sunshine. She was a B-24H variant, serial number 42-52106, and her journey from American assembly line to German test facility began with a routine mission that turned into anything but routine. On March 29, 1944, Lieutenant Gifford T. Hemphill guided Sunshine through the skies over northern Italy on a bombing run against Bolzano. The mission proceeded normally until it didn't. Somewhere over the Italian countryside, damage forced an emergency landing. Hemphill expected to set down in friendly territory. Instead, the wheels of Sunshine touched the ground at Venegono, Italy, behind German lines. The crew became prisoners of war. Their bomber became perhaps the most valuable intelligence prize of the European Air War. The Germans had captured American aircraft before. The Luftwaffe operated a specialized unit called Kampfgeschwader 200, tasked with evaluating and sometimes clandestinely operating enemy aircraft. Another unit, the Circus Rosarius, or Rosarius Circus, toured operational airfields throughout the Reich, demonstrating captured Allied planes to Luftwaffe pilots and training them in techniques to counter these aircraft. But Sunshine represented something special. The B-24H was the latest variant of the Liberator, incorporating improvements that German intelligence had only heard rumors about. Rather than sending this prize to a forward facility for quick assessment, the Luftwaffe designated it for comprehensive evaluation at Rechlin-Leertz, where Germany's best aviation engineers could conduct a thorough examination. The original film documenting the capture and examination would be preserved in the Bundesarchiv in Koblenz, a testament to how valuable the Germans considered this acquisition. The evaluation team that gathered around Sunshine included some of Germany's finest aeronautical minds. These men understood aircraft construction at the molecular level. They had designed fighters and bombers that represented the pinnacle of European engineering. They expected to find weaknesses in the American design, vulnerabilities that could be exploited, evidence that German craftsmanship remained superior even as the war turned against them. What they discovered instead would shake their professional confidence to its core. The surprise came not from what the aircraft could do. German intelligence already had reasonable estimates of the B-24's performance envelope. The surprise came from how it had been made. The external inspection began on a spring morning with engineers walking slowly around the bomber, notebooks in hand. German aircraft manufacturing employed skilled craftsmen who fitted parts with precision, filing and adjusting components by hand to achieve proper tolerances. Each Luftwaffe aircraft was, in a sense, handcrafted. The men examining the B-24 found something radically different. Every panel fit perfectly, not approximately correctly, perfectly, and there was no evidence whatsoever of hand fitting. The rivets marched in straight lines with mechanical precision. The aluminum skin showed no signs of adjustment, no file marks, no evidence that human hands had shaped any individual piece to fit its neighbor. Each component had simply been manufactured to such precise specifications that it slid into place exactly as designed. They moved to the control surfaces. German practice required mechanics to adjust each aileron, each elevator, each rudder to achieve proper response characteristics. The adjustments varied from aircraft to aircraft because no two aircraft came off the line exactly alike. On Sunshine, every control surface operated within identical parameters. The engineers checked their instruments, they checked them again. The implications were staggering. The Americans had achieved manufacturing tolerances that eliminated the need for individual adjustment. This wasn't just efficiency. This was an entirely different philosophy of aircraft production. The investigation proceeded into the aircraft's interior. Here, the German engineers expected to find complexity, the kind of bespoke craftsmanship that characterized European aviation. What they found instead were standardized components, each marked with part numbers, each apparently identical to its counterparts on every other B-24 in existence. Damaged components could simply be removed and replaced with new ones pulled from inventory. No adjustment required, no skilled craftsman needed to make it fit. The maintenance implications alone suggested an operational flexibility that German ground crews could only dream of achieving. The engines provided perhaps the most dramatic evidence of what the team had begun to call the American production philosophy. Sunshine carried 4 Pratt & Whitney R1830 Twin Wasp radial engines, each producing 1,200 horsepower. German engineers were familiar with these engines from previous examinations of captured aircraft. The technical specifications held no surprises. What struck them was the construction quality. Each R1830 had been built entirely to specification, using exactly the materials originally specified with no substitutions or compromises. German engine production by 1944 had been forced into constant material substitutions as strategic resources became scarce. Aluminum alloys were replaced with inferior alternatives. Precision bearings were manufactured from whatever steel was available. Each substitution degraded performance and reliability. The American engines showed no such compromises. They were built exactly as designed, every single one of them, in quantities that German industry could no longer match. But the wings drew the most intense scrutiny. The B-24 Liberator owed its remarkable range and speed to a design feature that had puzzled aeronautical engineers since its introduction, the Davis wing. Named after David R. Davis, a freelance aeronautical engineer who had developed the design in the 1930s, this wing represented one of aviation's great paradoxes. According to established aerodynamic theory, it shouldn't have worked as well as it did, and yet thousands of B-24s flew millions of miles on wings that conventional wisdom suggested were fundamentally flawed. The story of the Davis wing began in the summer of 1937 when Davis approached Reuben H. Fleet, president of Consolidated Aircraft, seeking funding to develop his unconventional airfoil design. Davis called it the fluid foil. He had designed the profile in reverse, starting with a basic low-drag teardrop shape and then modifying it to provide lift. The approach was counterintuitive. Conventional wing design began with lift requirements and then tried to minimize drag. Davis began with minimal drag and then figured out how to generate lift. The result was a wing profile that was relatively thick with a short chord while still being deep enough to allow a high aspect ratio. Davis claimed the new wing would offer reduced drag over contemporary designs and considerable lift even at small angles of attack. Fleet and his chief engineer, Isaac M. Ladden, were initially unimpressed. Davis was an outsider, a freelance designer approaching one of America's largest aircraft manufacturers with claims that seemed too good to be true. But a few days after the initial meeting, Ladden changed his mind. He convinced Fleet to pay for construction of a model and wind tunnel testing at the California Institute of Technology. The intention was to compare Davis's design against one developed in-house at Consolidated. What happened next entered aviation legend. The initial results from the Caltech wind tunnel were disappointing. Test instruments did not support Davis's predictions. The wing appeared to perform no better than conventional designs. But Davis refused to accept the results. He argued that Caltech's instruments, despite being among the most sophisticated in the world, were not sensitive enough to detect the improvements his design offered. This was an audacious claim. Davis was essentially telling one of America's premier research institutions that their equipment wasn't good enough to measure his innovation. Remarkably, investigation proved him right. After recalibration of the wind tunnel instruments, new tests showed dramatically improved readings. The Davis wing delivered everything its inventor had promised, and then some. The results were so exceptional that Caltech engineers were skeptical. They recalibrated and ran the tests a second time, then a third time. When they finally delivered their report to Consolidated, it indicated that the wing appeared to deliver outstanding performance, but with a significant caveat. The scientists suggested it might be a wind tunnel fluke, a design that gave excellent results only in controlled laboratory conditions, but might not perform in the real world. Wind tunnel walls affected results by increasing effective aspect ratio, and the Reynolds numbers used might have been incorrect. Fleet decided to take the gamble. He authorized the Davis wing for Consolidated's new twin-engine flying boat, the Model 31 XP-4Y Corregidor. The aircraft made its first flight on May 5, 1939, and immediately vindicated Davis's design. The wing performed exactly as promised in actual flight conditions. By that point, Consolidated was already working on a secret project for a new heavy bomber intended to improve upon the Boeing B-17 Flying Fortress, which was just entering service. The Davis wing was selected for this project as well. The Model 32, which would become the B-24 Liberator, first flew on December 29, 1939. The German engineers examining Sunshine understood the Davis wing's specifications. With its high aspect ratio of 11.55, a wingspan of 110 feet, covering just over 1,048 square feet, it represented a dramatically different approach than the wider, thicker wings of contemporary bombers, like the B-17 or their own Hauptwand-Rundflugzeugers. The wing maintained laminar flow across 20 to 30% of the chord, compared to just 5 to 20% for conventional designs of the era. This extended laminar flow was the secret to the wing's efficiency. Air moving smoothly over the wing surface generated less drag, allowing higher speeds and longer range for a given fuel load. But laminar flow came at a cost. The wing's thin profile and the precise shape required to maintain that smooth airflow meant the structure was inherently more fragile than conventional designs. The Germans noted that fuel tanks were built directly into the wing skin, which was less than 1/10 of an inch thick in places. This saved weight and maximized fuel capacity, but it also meant that even minor damage could cause leaks or fires. The narrow wing design required higher stall speeds, forcing pilots to keep the aircraft fast during takeoff and landing. In rough weather or when hit by enemy fire, the wing could twist violently, leaving almost no safety margin. The engineers performing the evaluation noted something else about the Davis wing. According to their calculations, the structure should have been more vulnerable to combat damage than it appeared to be in practice. German fighter pilots reported that B-24s could absorb significant punishment and continue flying. Yet the thin wing, with its fuel-filled interior, seemed theoretically more susceptible to catastrophic failure than the B-17's stubbier but sturdier wing design. The mathematics said the wing shouldn't have worked as well as it demonstrably did. This wasn't mysticism. The Germans simply couldn't reconcile their theoretical models with the empirical evidence flying over their heads daily. Part of the answer lay in the production quality they had already observed. The Davis wing's efficiency depended on maintaining precise aerodynamic contours. Any imperfection in manufacturing, any deviation from the specified shape, would disrupt laminar flow and degrade performance. Even small dents or ice accumulation on the wing surface could destroy the laminar effect. German engineers understood this, and it led them to assume that actual production models would perform worse than test prototypes. Each manufactured wing would have slight imperfections that would reduce its efficiency. What they discovered examining Sunshine upended this assumption. The wing was manufactured to tolerances so precise that it maintained near-theoretical performance even as a production model. The Americans had somehow industrialized perfection. They had taken a design that demanded exactitude and figured out how to produce it by the thousands without degradation. This was the true achievement that the German evaluation team struggled to comprehend. The Davis wing worked not despite its demanding requirements, but because American industry had risen to meet those requirements on a scale previously thought impossible. The landing gear provided another window into American engineering philosophy. The B-24's nose wheel had a reputation among crews for weakness. It collapsed more easily than pilots would have liked, particularly during rough landings or on unprepared fields. The German engineers examining the system understood exactly why. The Americans had deliberately designed the landing gear to standard specifications, knowing it would occasionally fail, but accepting that failure rate in exchange for manufacturing simplicity. A German engineer would have over-engineered the component to ensure it never failed. The Americans had instead done a cold calculation. A slightly higher rate of landing gear failures was acceptable if it meant every component came off the same production line to the same specifications, simplifying supply chains and enabling faster production. This was not inferior engineering. It was a different kind of engineering, one optimized for industrial warfare rather than individual aircraft performance. The men conducting the evaluation began to understand that they were not simply examining an enemy bomber. They were examining evidence of an entirely different approach to waging industrial war. Each discovery pointed toward the same conclusion. The Americans had designed this bomber assuming they would build thousands of them. Every component, every system, every structural element reflected an engineering philosophy that prioritized ease of manufacturing and maintenance over theoretical optimization. This was mass production applied to the most complex machines humans had ever built, and it worked. If you're finding this exploration of wartime engineering fascinating, now would be a great time to subscribe for more deep dives into military history. Your support helps us continue bringing these stories to life. To understand the full implications of what the German engineers discovered, one must understand where B-24 Liberators came from. The bomber that sat on the tarmac at Rechlin-Lers had likely rolled off an assembly line that represented the most ambitious industrial undertaking in human history up to that point, the Ford Willow Run plant. When the United States War Department approached Ford Motor Company about building B-24 bombers, the automaker's response was characteristically ambitious. Ford would not simply manufacture aircraft the way other companies did. Ford would apply the same mass production techniques that had revolutionized automobile manufacturing to the construction of heavy bombers. The result was a facility unlike anything the world had seen. Construction began on April 18, 1941, on farmland about 30 miles west of Detroit, Michigan. The numbers involved defied comprehension. Workers poured over 100,000 yards of concrete. They erected 38,000 tons of structural steel. They set 10 million bricks, fitted miles of piping, and ran more miles of electrical cable to operate the thousands of machines that would fill the structure. When completed, the Willow Run plant covered 80 acres under a single roof, with an assembly line stretching over a mile in length. The plant that emerged was designed around a single principle: continuous flow production. Where other aircraft manufacturers assembled bombers at stationary positions, moving parts and workers to the aircraft, Willow Run moved the aircraft through the workers. B-24s began as raw materials at one end of the enormous building and emerged as flyable bombers at the other end, having traveled through hundreds of production stations where specialized workers performed specific tasks with mechanical efficiency. The early months were difficult. Ford's engineers discovered that building bombers was fundamentally different from building automobiles. There were no usable blueprints from Consolidated Aircraft, the original designer. Ford engineers had to reverse engineer thousands of bomber part drawings before an assembly line could be set up. At one point, engineers were creating miles of technical schematics every day just to keep the production design process moving forward. Critics in Washington and the press began calling the facility "Will It Run," mocking its failure to meet production targets. But Ford persisted. Problems were identified and solved. Procedures were refined. Workers gained experience. Slowly and then rapidly, production climbed. By 1944, Willow Run had transformed from industrial embarrassment to industrial miracle. The peak came in April of that year, the same spring that German engineers were examining sunshine at Rechlin-Lers. In April 1944, employees working 2 9-hour shifts, 6 days a week, produced 453 B-24 Liberators in 468 hours. That production rate worked out to one finished heavy bomber every 63 minutes. Charles Sorensen, Ford's production chief, had promised a bomber every hour. Critics had dismissed the claim as industrial fantasy. Now Willow Run was exceeding that promise. At full operational capacity, Willow Run produced 650 B-24 Liberators in a single month. By 1945, despite there being 2 other Liberator production plants operated by other manufacturers, Willow Run alone accounted for 70% of all B-24 production. Pilots and crews slept in a dormitory with 1,300 cots, awaiting the near-hourly birth of new bombers. Each 4-engine bomber contained roughly 1,225,000 parts. Every single part had to be manufactured, transported, and assembled correctly. And yet one rolled off the line every hour. The total numbers tell the story in stark terms. A total of 18,482 B-24 Liberators were built by September 1945, making it the most produced American military aircraft of the war. Willow Run alone delivered 8,700 of those bombers. One factory, operating for less than 4 years, had produced nearly half of America's most important heavy bomber type. This was what the German engineers were really discovering when they examined Sunshine. Each perfectly fitted panel, each interchangeable component, each precision-machined part represented not just a single bomber, but an entire industrial ecosystem capable of producing more bombers than Germany could hope to shoot down. The evaluation team had the technical training to understand the aerodynamic principles behind the Davis wing. They had the expertise to assess the bomber's combat capabilities. What they struggled to process was the evidence that one aircraft implied thousands more identical to it, rolling off assembly lines in quantities that rendered traditional concepts of attrition warfare meaningless. By May 1944, the evaluation team had completed their technical assessment. The report they prepared ran to over 300 pages of detailed analysis covering every aspect of the B-24's design, construction, and potential vulnerabilities. But the conclusion could be summarized in a few brutal sentences that must have been difficult to write, and even more difficult to read at Luftwaffe headquarters. The B-24 Liberator, the report stated, represented not superior aircraft design, but superior production engineering. German fighters could shoot down B-24s. German flak batteries could tear them from the sky. But the Americans could replace losses faster than Germany could inflict them. The scale of American manufacturing capacity, as evidenced by this single aircraft type, suggested that victory through material attrition was no longer achievable for Germany. The engineers who had spent weeks measuring rivets and analyzing wing structures had reached a conclusion with implications far beyond aeronautics. The war was lost, and the evidence was in the perfect fit of interchangeable parts. The report was forwarded through Luftwaffe command channels. The cover memo noted that the findings were consistent with similar reports from examinations of other American equipment. This was not an isolated revelation. German technical intelligence had been accumulating evidence of Allied production superiority for months. Each captured tank, each recovered engine, each downed aircraft told the same story in different ways. The Sunshine evaluation simply provided the most comprehensive, single documentation of what many German professionals already suspected. Albert Speer, the Reich Minister of Armaments and War Production, had reached similar conclusions through different paths. In his memoirs, he would characterize Germany's approach to industrial production as outmoded, tradition-bound, and arthritic. The German system relied on skilled craftsmen producing relatively small numbers of high-quality items. The American system treated aircraft like automobiles, designed from the start for mass production, with quality achieved through precision tooling and standardized processes rather than individual craftsmanship. Both approaches could produce excellent aircraft, but only one approach could produce enough aircraft to overwhelm the other. The implications extended beyond mere numbers. The B-24's interchangeable parts meant simplified supply chains. A replacement component manufactured in Michigan would fit a bomber operating from England or Italy or India without modification. German aircraft required components specifically fitted to individual machines. Logistics officers had to track not just part types, but specific serial numbers and their destinations. The Americans could ship standardized parts by the crate and let maintenance crews pull what they needed. The cumulative effect of these simplifications was an enormous multiplier in operational capability that no amount of German engineering excellence could match. The captured bomber that had sparked this evaluation would go on to serve the Luftwaffe briefly. Sunshine was assigned to Kampfgeschwader 200, the secret operations unit that employed captured Allied aircraft for various clandestine purposes. 3 B-24s in total were captured and operated by KG 200 during the war. One had been seized at Vennegono. These aircraft were repainted in Luftwaffe markings and used for penetration missions, flying in Allied bomber streams at night to gather intelligence, or in some cases, to attack targets of opportunity while disguised as friendly aircraft. The irony of Sunshine's end would have appealed to any student of military history. On April 6, 1945, as the Reich collapsed around it, the captured B-24 was being ferried from Hildesheim to Bavaria, presumably to prevent its capture by advancing Allied forces. Somewhere over Germany, German anti-aircraft batteries opened fire on the aircraft. The gunners apparently saw only the silhouette of an American heavy bomber. They did not recognize that this particular B-24 wore German markings. Sunshine was shot down by friendly fire, destroyed not by the enemy, but by the collapsing command structure of the nation that had captured her. The bomber that had revealed so much about American industrial might end its existence as evidence of German organizational disintegration. But the insights gained from examining Sunshine and aircraft like her came too late to change the course of the war. The strategic bombing campaign that brought B-24s over German territory daily continued to intensify throughout 1944 and into 1945. Formations of 50, 100, sometimes 500 bombers struck targets throughout German-held territory. Losses that would have crippled earlier campaigns were absorbed and replaced within days. German intelligence tracked B-24 units operating simultaneously from England, Italy, North Africa, India, and Pacific bases. The bomber the evaluation team had so carefully studied was just one of thousands performing the same mission across multiple theaters of war. The Davis wing that had puzzled the German engineers continued to carry those bombers to their targets. Its theoretical fragility proved less decisive in practice than the calculations suggested. Yes, the thin wing was more vulnerable to certain types of damage than the B-17's more conventional design. Yes, some B-24s suffered catastrophic wing failures when hit by anti-aircraft fire, but enough of them survived, enough of them delivered their bombs, and enough of them returned to fly again that the mathematical vulnerabilities mattered less than the strategic realities of mass production. The Liberator's combat record demonstrated both the capabilities and the costs of this approach. Operation Tidal Wave, the low-level raid against the Ploiești oil refineries in Romania on August 1, 1943, showed what B-24 crews faced and what they could endure. 178 B-24 Liberators took off from Benghazi, Libya, for the 1,000-mile flight to the most heavily defended industrial target in Axis territory. The plan called for a surprise low-level attack, coming in under radar coverage to strike the refineries before defenses could fully respond. The mission began falling apart almost immediately. Clouds broke the formation into separate groups as the bombers crossed the Mediterranean. A navigational error caused further confusion as aircraft approached the target. By the time the B-24s reached Ploiești, the element of surprise was gone. German and Romanian defenders had scrambled fighters and manned anti-aircraft positions. The bombers came in at treetop level, exactly as planned, and flew directly into a hurricane of fire. The scenes over Ploiești that day would haunt survivors for the rest of their lives. B-24s flew so low that their propellers kicked up dust from the ground. Explosions from bombed refineries created walls of flame that following aircraft had to fly through. One B-24, nicknamed Jose Carioca, was attacked by a Romanian IAR-80 fighter that performed a half-roll, slid under the bomber inverted, and raked its belly with bullets. The Liberator crashed directly into the Ploiești women's prison, killing about half of the 101 civilians who died in the raid. 40 women in the prison survived. None of Jose Carioca's crew did. When the shooting stopped and the surviving bombers turned for home, the cost became clear. 54 B-24s were lost over the target and on the return flight. Nearly 500 airmen failed to return, with 310 killed and 186 captured. The loss rate approached 30% for a single mission. 5 Medals of Honor were awarded for actions during the raid, 3 of them posthumously. It was the costliest mission in the history of American military aviation up to that point. And yet the bomber force recovered. Replacement aircraft flowed from Willow Run and the other production facilities. New crews completed training and joined the operational units. Within weeks, B-24 groups were flying combat missions again, their numbers restored. The Ploiești refineries would be struck again and again over the following year, ultimately reducing Romanian oil production to a fraction of its former capacity. The Germans had inflicted terrible losses on that first August day, but they could not inflict losses faster than the American industrial machine could make them good. The men who flew these bombers understood the bargain they had accepted, even if they didn't think of it in those terms. The B-24 traded certain safety margins for range and payload capacity. Its pilots knew the aircraft demanded precise handling. Landing speeds exceeded 100 miles per hour. A sudden loss of lift could send the plane into an unrecoverable spin. Training accidents were common, and crews quietly nicknamed the bomber the Widowmaker. But they also knew the Liberator could carry them to targets no other American bomber could reach, and bring them home across distances that would have grounded lesser aircraft. The structural vulnerabilities of the Davis wing claimed lives throughout the war. Some bombers that took flak damage experienced catastrophic wing failure, the thin structure giving way under combat stress. Others crashed on takeoff or landing when pilots misjudged the aircraft's demanding handling characteristics. The statistical reality was stark. It is estimated that only about 25% of bomber crews completed their 25 mission tours without being killed, wounded, or captured. The B-24's loss rate per sortie was actually slightly lower than the B-17's, but thousands were lost nonetheless. But those who survived often credited the very features that made the aircraft dangerous. The long range meant bombers could approach targets from unexpected directions. The high cruising speed meant less time exposed to fighter attack. The large payload meant each mission delivered more destruction per aircraft. And the incredible production numbers meant there were always more bombers, always more crews, always more bombs falling on targets that German industry desperately needed to keep operating. The Davis Wing's advantages proved situational. Its laminar flow characteristics worked only when the wing surface was clean and smooth. Ice accumulation could destroy the effect, causing sudden increases in drag and decreases in lift. Even small dents from minor damage could disrupt airflow. Crews learned to watch their instruments carefully when flying through precipitation. The wing that gave them such efficient cruising could become dangerously unpredictable when conditions deteriorated. These limitations contributed to the decision not to use the Davis Wing in post-war designs. Although it represented a genuine innovation and taught aeronautical engineers valuable lessons about laminar flow, the wing's advantages were too marginal and too dependent on perfect conditions to justify its disadvantages. The thick profile that Davis had designed for low-speed efficiency also created problems at higher speeds, where wave drag became significant. As aircraft speeds increased in the jet age, the Davis Wing's reduced low-speed drag could not compensate for its increased high-speed drag. The design that had been revolutionary in 1939 was obsolete by 1945, but for the duration of the war, the Davis Wing did exactly what Consolidated and the Army Air Forces needed it to do. It carried heavy loads over long distances at speeds that kept pace with escort fighters. It gave America a strategic bomber capable of reaching any target in Axis-held Europe from bases in England and Italy. It enabled the closing of the mid-Atlantic gap where German submarines had once found sanctuary from land-based patrol aircraft. The B-24 delivered a larger share of American bomb tonnage than any other bomber type and helped strangle the German war economy in the final year of the conflict. The German engineers who examined Sunshine understood all of this at a technical level. What made their report so significant was not its technical analysis, but its strategic conclusion. They recognized that they were looking at evidence of industrial warfare, a type of conflict that Germany's craft-based manufacturing system could not win. The Davis Wing worked because American factories could build it precisely enough and in large enough quantities. The bombers kept coming because Willow Run could produce one every 63 minutes. The war was being won not in the air over Germany, but on the assembly lines of Michigan. This realization spread through German military and industrial circles throughout 1944. Speer attempted reforms to rationalize German production, but years of fragmented industrial organization could not be overcome in months. German factories continued producing excellent weapons in inadequate quantities. American factories produced good enough weapons in overwhelming quantities. The mathematics of attrition pointed toward only one possible outcome. The legacy of the B-24 Liberator and its controversial Davis Wing extends beyond the war itself. The aircraft demonstrated that unconventional designs could succeed when backed by sufficient production capability. David Davis had been a freelance engineer with an idea that established wisdom said shouldn't work. But wind tunnel tests proved his concept viable, and American industry proved it could be built at scale. The combination of innovative design and industrial might created a weapon system that changed the course of history. The men who flew these bombers became part of that legacy, whether they survived the war or joined the 30,000 who did not return. They climbed into aircraft they knew were dangerous, flew missions they knew might be their last, and trusted that the thin, efficient wings would carry them to the target and back. Many times those wings failed. Many times they did not. The B-24 demanded everything from its crews and gave them the tools to strike at the heart of enemy territory in return. For German engineers standing before a captured Liberator in the spring of 1944, the aircraft represented something more than an enemy weapon. It represented evidence that the industrial war was already lost. Every perfectly fitted panel, every precisely machined component, every interchangeable part testified to a production capacity that no amount of German engineering excellence could overcome. The wings shouldn't have worked according to their calculations, but there they were, carrying bomber after bomber across the Atlantic and back again in numbers that made theoretical vulnerabilities irrelevant. The war would continue for another year, costing millions more lives before the final collapse. But the outcome was already written in the manufacturing tolerances of a captured bomber at Recklinlerz. The Davis wing might have looked fragile on paper. American industrial might was anything but. If this documentary helped you understand a fascinating chapter of aviation and military history, please consider subscribing and sharing with others who appreciate these deep explorations of the past. Thank you for watching, and we'll see you in the next video.